Hi, welcome to this video. In this class, we discuss some more reactions of carboxylic acids. In the previous video, we were discussing about the most important reactions of carboxylic acids where the OH group of carboxylic acid is replaced by various groups forming what are called acid derivatives like ester, amide, acid halide and acid anhydride. Here we have some special reactions, mainly three. The first one is HVZ reaction, that is Halogenation reaction. It is simply alpha halogenation. You can see a common reaction RCH2COOH. You know, this is alpha position with respect to this acid. This alpha carbon is highly reactive. You might have learned this in aldehydes and ketones or any carbonyl compounds. Due to the resonance property of this carbonyl group, there is chance for enolization, and so this carbon is highly reactive. This hydrogen can be easily replaced. Okay, so aliphatic carboxylic acid treated with halogen X2 in presence of small amount of red phosphorus. Halogen is generally chlorine or bromine, and you get the product, that is alpha halo carboxylic acid. Okay, now putting a specific example, let me take CH3CH2COOH. This is propanoic acid. It is treated with, say, for example, bromine in presence of red phosphorus. One of the alpha, this is alpha carbon, this is beta carbon, this get replaced, so you get the product CH3 CHBrCOOH. The product is alpha bromopropanoic acid. Now here, if you are using excess of chlorine, excess of halogen, for example, let me take CH3COOH treated with excess of chlorine, for example, chlorine in presence of phosphorus, alpha halogenation takes place successively. That means first you get CH2ClCOOH, that is monochloro product, alpha chloro ethanoic acid or acetic acid. If you continue using more chlorine, more and more alpha hydrogen get replaced. So next you get CHCl2, one more H is replaced by Cl. Of course there is byproduct HCl, you can write it like this also, minus HCl. So you have dichloroacetic acid, and finally you get CCl3COOH. So here minus HCl, here also minus HCl. So you get finally trichloroacetic acid or ethanoic acid. So that happens. Then what is the role of phosphorus here? That's a good question. You can understand the role of phosphorus when we look into the mechanism of this reaction. What is the mechanism? That's very important. Let us go to the mechanism now. Mechanism of this HVZ reaction. It takes place mainly in three steps. First of all, this if you take generally, okay, let us consider this reaction in general and write the mechanism of this general reaction. So what happens is first these two react. Okay, that's not part of the mechanism. Generally, it is something which takes place in situ in the reaction site. X2 plus phosphorus forms PX3. Okay, phosphorus trihalide, maybe it's chloride or whatever. You can balance it, try putting 2 and 3 here. So it is 2PX3. That is the. Now the first step of the reaction is this react with this carboxylic acid. So RCH2COOH reacts with PX3 Now this is a reaction familiar to you, where that is in the formation of acid halide in the previous class. We know we can use BH3. So what is the product? You get RCH2COX, isn't it? And when you use PX3, you know the byproduct is H3PO3, isn't it? You refer back. And this can be balanced if you want, putting 3 here and 3 here. Okay, that's not a matter. So this is the first step. The first step of the mechanism of HVZ reaction is formation of acid halide. So this is acid halide. Okay. Now this acid halide is able to have enolization because of this. Now see, when it is become acid halide, it become more reactive. Already CO is electron withdrawing, and when X comes, the halogen it is strongly withdrawing. So that will make this carbon highly reactive or highly acidic, you can say. Or it can be, hydrogen can be easily replaced. So what happens is this undergo enolization. This is the keto form, right? And what is the enol form? So to understand that, let me write this in this way. H is shown separately, and this CO group also can be shown separately like this. So you know what happens in this enolization. This bond shift here, this pi electron move to oxygen, and this H plus will attach here. So what do you get? Now it is RCH double bond COH, correct? X. This is the enol form. Okay. So enolization takes place. Now comes the second step. What happens now? Now halogen comes in and react. Okay. Halogen comes in and reacts. So what is the role of phosphorus in this reaction? It is to convert carboxylic acid into more reactive acid halide, and which undergo alpha halogenation. So now this is again shifting here. This pi electron moves to this carbon, and this halogen will break, produce Br minus and Br plus, which will attach here, and you get the product. So it is now CHBr, sorry, not Br, it is X, generally short, X here. Then single bond, C double bond O, X. Okay, and this H will attach with, H plus will attach with this X minus, producing HX. So minus HX I can write here. So you got this one. What is this? This is an intermediate, not the product. What is this? This is alpha halo acid halide or acyl halide. Alpha halo acid halide. Okay. Now in the final step, see, this is the third step. What is the third step? Now this molecule react with another molecule of unreacted, acid. So this alpha halo acid halide react with another molecule of carboxylic acid and undergo what is called exchange reaction. So here takes place an exchange reaction. What exchange? This halogen will be exchanged with this acid. It will go to this one and you get the product. So what is the product? You get now the product as RCHXCOOH, where X has gone to this molecule of acid and it becomes acid halide. RCH2COX. You understand? See what has happened? This X gone to this one. Okay, OH is replaced. OH and X has exchanged. Advantage is that this one is now again come back to the step. Second step here. This step, and it can further react. Okay, so the mechanism has two, actually there are 3 steps. This is second step and this is the third step. You understand? So that's the mechanism of HVZ reaction. Okay, now we move to the applications of HVZ reaction. See, what is the best part of HVZ reaction? This is the route to prepare. This is the route to prepare alpha substituted compounds. Okay, see, if you want to introduce various functional groups at this alpha position, the best route is you introduce halogen and you can change it by various functional groups, because you know this is more this is something like alkyl halide only, and alkyl halide can undergo various SN reactions using various nucleophiles, and also it can undergo elimination reaction also, forming various products. So let us summarize the applications now. Here we can take, for example, suppose we have prepared this alpha bromo propanoic acid. Okay, this can be converted into various products. If you are treating with NH3, that means various nucleophiles we are using, ammonia can react with this, it can substitute this Br and form alpha amino product. So that is number 1. So it is NH2 here, COH. So alpha amino acid is obtained, and of course you will have the byproducts, that is that will be HBr. The next one is, if you are using aqueous NaOH, what do you get? Aqueous NaOH. You know the nucleophile is OH minus, so Br will be replaced by OH minus. It's a kind of hydrolysis, and you get the product, that is alpha hydroxy acid. Remember, if you heat it, it can lose water and form double bond here. You get alpha beta unsaturated acid. Okay, that is an extension of this reaction. Now, another reaction is, if you use NaCN, you know, Cn minus is a nucleophile, so that is used for preparing nitrile. So that will react here, and Br is replaced by Cn. So it is CH3, CN, COH. See, you can extend this reaction for what? You know, we already learned Cn can be hydrolyzed to get what? Acid. So you can get dicarboxylic acids, right? And finally, if you are using alcoholic KOH, what is the reagent alcoholic KOH for? That is for elimination of alkyl halides. So what happens? HBr will be lost from alpha beta position, and double bond comes here. So CH2 double bond CH, COOH. Okay, so these are various synthetic applications of HVZ reaction. Okay, now we move on to the next one. The second type of reaction we discuss here is decarboxylation. Okay, decarboxylation. In that there are two. One is soda lime heating. You can see. What is soda lime heating? If sodium salt of carboxylic acid is fused, heated strongly with soda lime. What is soda lime? Soda means sodium hydroxide, lime stands for calcium oxide, and that in 3:1 ratio. So it's a mixture of NaOH and calcium oxide in 3:1 ratio, that is called soda lime. Sodium hydroxide is used for taking CO2, for decarboxylation. It can absorb CO2 and form sodium carbonate. Calcium oxide is added to keep NaOH dry, otherwise it is deliquescent. Okay, so we can write, so what is the product here? See, it's very simple to understand. This is what happens. This is what happens. What is it? Na2CO3, the carboxylate group is taken by NaOH, and H will attach here. So you get the product, that is an alkane. You get an alkane plus sodium carbonate. So the reaction is sodium salt of carboxylic acid when fused with soda lime gives alkane with one carbon less. See, so this is the interesting part of this reaction, is that it is stepping down, descending series. If you want to remove one carbon, this is the route. So this carbon is lost in terms of carbon dioxide plus sodium carbonate. Okay, we'll see the mechanism of this reaction. Let us take a particular example for this decarboxylation. For example, CH3, CH2, COONA. So for this you need sodium salt of the acid. If you have the acid only, of course it will react with NaOH and form sodium salt. Doesn't matter. So this is heated with soda lime, NaOH calcium oxide heating. So what happens? As I said, this is what happens. What is the product here? You get CH3, CH2NH will be added and you get ethane plus sodium carbonate. So this is soda lime heating. Okay. This equally applies to, aromatic acid also. For example, if you are taking benzoic acid, okay, benzoic acid can be converted into benzene. It's a very interesting conversion. Benzoic acid is converted to benzene. How? You convert it into the sodium benzoate and then fuse with NaOH soda lime, calcium oxide, soda lime, heated with soda lime, so that this carboxylic acid group can be expelled. Now coming to mechanism. Let us see the mechanism of this reaction. It's very simple mechanism only, nothing big. See, this is a general reaction. Let me consider this RCOONA. Okay. So this carboxylate ion, what happens is that it is a carboxylate ion which takes part in this reaction. So the reaction is like this. This lone pair will form double bond here, so that this bond will be shifting heterolytically, breaking in favor of this alkyl group. Okay, so that it become R minus with a lone pair. That means it become a carbanion plus a stable CO2 molecule. So carbon dioxide is lost in this way from this molecule, and it will be taken up by NaOH, which is a strong base. CO2 is acidic oxide, so it is reacting with NaOH. So this is carbanion. Okay, that's the first step. Now this intermediate now take up H plus from water or any protic medium. It can take H plus and becomes RH. That is the product, and OH minus as the byproduct. It is lost. It is removed. So you get this alkane in this way. That's the mechanism of this soda lime heating reaction. Okay. So the best part of this reaction is that it is used for reducing one carbon from the parent carboxylic acid. Now finally, we have another method of decarboxylation, that is Cope's electrolysis, an electrolytic method. What is the reaction? See, sodium salt of carboxylic acid is electrolyzed. Electricity is passed in an aqueous solution, and a concentrated aqueous solution has to be used, and it can be sodium or potassium salt. It has to be highly ionic, a good electrolyte. And when you pass current, what happens? You get an alkane. This is an alkane obtained at anode. Alkane is obtained. So interesting part is that if you are using RCOOH, that's the acid, this carbon is lost, but this R is doubled. So the number of carbon become even. That is the limitation of this method actually. Always you get an alkane of even number of carbon. Actually, these reactions would have come in the preparation of hydrocarbons in your 4th semester, right? You may recall that. And these are the byproducts. CO2 is there, NaOH is there, and what is the product at cathode? Hydrogen is obtained. Putting an example for this reaction, or we can understand how this reaction has taken place like this. I am writing this RCOONA. 2 molecules are reacting here. So let me write 2 molecules of RCOONA, and 2 molecules of water also take part here. I can write this water like this. Okay, OH and H. Now the reaction can be easily visualized like this. See, this is how. See, what you get? You get RR, that is an alkane, a saturated hydrocarbon, then 2 molecules of CO2, 2 molecules of NaOH and 1 H2. Correct? This is understandable. Now we can take a specific example. For example, if you are taking sodium acetate and carrying out this electrolysis, what do you get? 2 molecules will react with 2 molecules of water, and what do you get the product? CH3CH3, that is ethane, is obtained, plus, as here you get 2 CO2 plus 2 NaOH. These are the byproducts, and hydrogen is also obtained, right? So that's the reaction. Now coming to mechanism and limitation. What is the mechanism of this reaction? See, it's only electrolysis, so you have to explain what is the anode reaction and cathode reaction. That's all. So in this solution, you are taking a concentrated aqueous solution of sodium or potassium salt of carboxylic acid. So the solution will contain RCOO minus, that is one anion, and there will be Na plus, that is cation. In addition, it will contain water molecule also. So to consider all these species for electrolysis, at anode, the reaction at anode is, that is the main reaction here, this RCOO minus, that is a carboxylate ion, undergo oxidation. In electrolysis, oxidation takes place at anode. That means it will lose electron. It will lose one electron only, okay, and it become what? It become a carboxylate radical. It become, see, it's minus here means there is a lone pair. If it lose one electron plus one electron, that negative charge will go and it become a radical end. This is oxygen become a radical. And for 2R has to combine, so to balance you will take 2 acetate and there are 2 radicals. So this is carboxylate radical. Now what happens, this will break away, means it is a homolytic fission. One electron is shifting here and it become a stable carbon dioxide molecule. So it is now, this, when CO2 is breaking away, it become R radical. You understand? This electron will be remaining, the unpaired electron, plus CO2. There are 2 molecules, so there will be 2R and 2 CO2. So you got now 2 alkyl radicals that will easily combine and become RR, that is the alkane is obtained. So you have this alkane obtained at anode. Now at cathode, what is obtained? At cathode, it is hydrogen formed. Can you say from where H2 is formed? What undergo reduction at cathode? At cathode reduction takes place. Which undergo reduction? Is it Na plus or H2O? In electrolysis of sodium chloride, you might have learned this. It is H2O which undergo reduction here based on the electrode potential. So H2O undergo reduction plus electron. What do you get? H2O can be assumed to be H plus and OH minus, and it is H plus which gets reduced and it become H atom or H radical, same thing, plus OH minus. If there are 2 molecules, it will be plus 2 electron and it will be 2H plus and 2OH minus, and now it is that this 2H radical can easily form H2. Just combining the 2 atoms, you get the product at cathode. So that's about the mechanism. Finally, what are the limitations of this Cope's electrolysis? There are 2. One is that you cannot prepare an alkane of odd number of carbon because always it is doubling, so it will be always even. Number 2, it is difficult to prepare an aromatic hydrocarbon using this method. That means if R is a benzene ring, okay, if it is sodium benzoate, it is difficult to break this, okay, it is difficult to form this radical, and it is strongly bonded, and decarboxylation is difficult in the case of carboxylic, aromatic carboxylic acid. Now finally, there are 2 questions to you. You should practice this. You should write the answer for this. Number 1, this is conversion. You have to convert. The question is to convert. Conversion. phenyl acetic acid to this product, C6H5CHCOOH twice. And the second one, propanoic acid to be converted to butane, you have to write the conversion chart with proper reagents and proper steps. Okay? With this, that's for now, and we will continue in the next class. Thank you.